Okay, hello everybody. Okay, so in this module we're going to be looking at the steady state error. However, before we start talking about the steady state error, I want to go back and do an example on the time response characteristics. Now, in the previous module, we looked at the response characteristics of the discrete time system, and there is a nice graph in the book that shows the different characteristics of the response depending on the location of the pole of the system. So as you can see in this graph, if the pole, for instance, at negative 0.5, then the response of the system is going to look oscillatory, and it's going to have positive, negative, is going to oscillate between positive and negative. If the pole is at 0.5, it's going to be just a decaying exponential response that we have here. If the pole happens to be complex, which is, for instance, this pole here, then you can see it is a decaying response, and it also have an oscillation in it. If the pole happens to be outside the unit circle, then it's going to be increasing response. So this is an example of that. If it is on the unit circle, if it is at z equal to 1, then that corresponds to the unit step function. So therefore, it's going to be just a constant response. So you can see here, and also another example of the response when the poles are outside the unit circle is this one here. You see how it is oscillating, but it's increasing in magnitude. And you can see later on when we look at the stability, why if we have poles that are outside the unit circle, the system is going to be unstable. You see all these poles that are outside the unit circle, what's happening to their magnitude? They're increasing with time. All the poles are within the unit circle, they're going to be decaying. If they are on the right half side of the unit circle along the real axis, then they're going to be all having the same sign and just decaying. So this is an example of that, and this is an example of that. If they are on negative real axis, then they're going to have oscillation. And it is very easy to see that. So if I have, this is, for instance, might correspond to a negative 0.5 to the power of k. This is going to oscillate. It is going to oscillate, and it's going to have a z transform that is z over z plus 0.5. The pole is at negative 0.5. The response in time is going to be oscillating, positive, negative, positive, negative. If it is at positive 0.5, for instance, this one here is going to be 0.5 to the power of k. And this is going to have a z transform that is z over z minus 0.5. Okay. Now, of particular interest here is these two poles that we have here. These two poles have a real part and imaginary part. Now we're going to be looking at these more closely in this example that we're going to look at. So in this example, this is the MATLAB code. I'm going to be running a MATLAB code. This is the MATLAB code. You're more than welcome to copy it and change the values and look at how the system behaves and look at the different responses, modify the values, etc. But what we're trying to do in this example, I'm going to take a continuous time second order system, omega n squared over s squared plus 2 zeta omega n multiplied by s plus omega n squared, and I'm going to apply a step to this input, to this system. So the input is a unit step, and then I'm going to look at the output. Now we know from the previous class that the output of this system in the time domain is going to depend on the location of the the location of the poles of this system, and therefore is going to depend on the value of zeta, and that will determine whether we're going to have an underdamped response that might look like this, whether we're going to have a critically damped response that might look like this, or an overdamped response that might look like this. What is going to determine this is zeta. If zeta is less than 1, we're going to have an underdamped response. If it is zeta equal to 1, it's going to be critically damped, and if zeta is greater than 1, it's going to be an overdamped response. Now we did not derive the expression for, we listed the expression for the output in a table in the previous class. We did not derive it because we derived it in the previous controller class. Now what we want to do, I want to take this system, I want to convert it to a discrete time system. And therefore, I'm going to take this continuous time system that I have here. So this is my system here. This is the same system, the continuous time system. And I'm going to take this signal, I'm going to take it through the sampler, and then I'm going to take it through a zero order hold, and then through this system, and then I want to calculate y of z over r of z. Now to calculate y of z over r of z of this system, it is the z transform of the zero order hold and gp of s. Let's call this gp of s. This is gp of s. And therefore, it's going to be 1 minus e to negative st over s and omega n squared over s squared plus 2 zeta omega ns plus omega n squared. Now, what is the z transform of this? I can take 1 minus e to negative st out, and this will give me 1 minus z to the negative 1. I still have an s here that's going to be added to this expression. So I have this s that is coming from the zero order hold. And therefore, s multiplied by the gp of s. Now, how do I find the z transform of this? I can do it using the residual method, or I can go to the table that we have in the appendix and use the table. And the tables tell me I can use this table or this table depending on the value of the roots. But this will give me the expression for the z transform. This is the z transform. This is the z transform. This is if the poles of the continuous time systems are real, and this is if the poles of the continuous time system are complex. So I use the expression depending on the value of these roots. Okay, so therefore, if I do that, I'm going to get this expression for the transfer function, the transfer function between y of z and r of z. And of course, notice here that in the continuous time system, there was no zeros. Here, in the discrete time system, now I'm going to have a zero added to the transfer function. Okay. Now, of course, if you do this in MATLAB, let me see if we can see it in MATLAB. In MATLAB, I can, once I define the transfer function, I can tell MATLAB to use the command that is here, continuous to discrete, and I give it the numerator, denominator, the sampling time, and I'll tell it if I'm using zero order hold. And that will give me h of z, or the transfer function in the z domain. So again, you can run this and see it for yourself. Okay, so what I'm going to do, or what I've done here, is I looked at the case when the system is underdamped, therefore zeta is less than 1. And if you look here, this is the poles of the continuous time system. And you see here I have a pole, and unfortunately the font is too small to see it, but I'm using Octave. Okay, so we have two poles, one at negative 1.4 and then plus minus, the other root is around 7. Okay, so again, these two roots are going to give me, so I have two roots in the left half plane that belong to an underdamped response. I know they're underdamped because I have these two roots that have imaginary part. Now these two roots are going to map to two poles that are going to be also complex, and they're going to be like this. So going back to this graph that I have here, this is what we're looking at, and a case where similar to this green that we have in here. So here, these two poles that are from the continuous time, in the discrete time, they translate it to two poles that are complex, that are inside the unit circle. Now I have also two zeros. that are added as a result of this transformation. Now, if I look at the response of the system, this is an underdamped response. This shows me the response of the continuous time system and the response of the discrete time system. See these steps that are coming from the discrete time response of the system. And the sampling time that I use here is t equal to 0.1 second. So you see every 0.1 second I have a response, and this is the response of this system. Now also I looked at the case when it is an overdamped, and in this case if I look at the poles of the continuous time system, the poles are along the real axis, and therefore I know this is an overdamped response. Now these two poles that belong to an overdamped response resulted in two poles in the discrete time that are along the real axis. So you see in the previous case, a second order system results in complex poles that are within the unit circle. In the overdamped case, it resulted in two poles that are along the real axis. And therefore, I'm going to have two poles here. Now, if I look at the response of the system, this is an overdamped response. This is the response of the continuous time system. And this is the response of my discrete time system. And you can see the zero order hold impact. Okay, so I hope this example is clear. And I mean, the two things that I want to emphasize in here, I mean, there are several things that I want you to pay attention to. The first is, this is a second order system. When I took the Z transform, I have an S here. It became a third order. So there's this S that came from the zero order hold. The second thing, I added, there is zeros that are added to the discrete, to H of Z or T of Z, as a result of converting, or as a result of generating the Z transform of this continuous time system. And the other point I want you to also probably use is the appendix that we have at the end of the table that will help us to go from H of S to H of Z for different transfer functions, and then the impact of how the response of the system is when it is underdamped. So in this case, underdamped response, and how this underdamped response will results in poles that are complex, that are within the unit circle, and the response of this is going to be underdamped response. And an overdamped response where we have poles that are on the real axis, this is the S domain, and this results in two poles that are along the real axis within the unit circle. This is in the Z space. And this is an overdamped. Now it is apparent if these two poles keep getting closer to each other, eventually they're going to meet at certain location, and then I'm going to have a critically damped response. In that case, these two poles are also going to move to closer to each other, and they're going to overlap. And again, the poles are mapped according to Z equal to ST. Okay. Now the new topic that we're going to be looking at today is the steady state accuracy. And what we're going to be doing in this module is deriving the expression for the steady state error of the system. So if we consider a sample data system that we have here, we define the error signal, and I hope everybody is clear why we define this, the error signal. This is the error signal because what is this error signal equal to? This is equal to R minus Y. R is what I'm setting my system at, and Y is what my system response is. The difference between them is the error signal. If R and Y are different, then I have an error. If R and Y are equal, then this error signal is going to be 0. So therefore, the error signal is R minus Y of S. And what we're going to do is we're going to calculate the expression for the steady state error. Okay, so to do that, we're going to be calculating E of Z over R of Z, and then we can use the final value theorem, which is going to give me what the steady state value of the error signal as k goes to infinity. So in this case, in this example that we have here, E of S is equal to R of S minus G multiplied by E star. And therefore, if I take the star transform, E star is going to equal to R star minus G star multiplied by E star. If I move G star multiplied by E star to the other side and take E star as a common factor and divide by 1 plus G star, I'm going to get E star over R star equal 1 over 1 plus G star. Okay, so therefore I can calculate E of Z over R of Z is going to equal to 1 over 1 plus G of Z. Now some comments on this G of Z. G of Z implicitly includes the zero order hold. G of Z equal to Z transform of G of S, and therefore it already includes the zero order hold. G of Z is the zero order equivalent discrete time model of G of S. So if you look here, I did not explicitly draw a block for the zero order hold, so we included the zero order hold with G of S. Okay. Now this pulse transfer function G of Z can be expressed as, we can expand it as the multiplication of the poles location, the zero locations over the poles locations. So I can write G of Z that I just calculated as a constant and multiplied by Z minus Zi from I equal to 1 to M over the multiplication of Z minus P sub J from J equal 1 to P. Now what I'm going to do is I'm going to take any factor that is Z minus 1 out of all this multiplication. And therefore, I'm going to write it as Z minus 1 to the N multiplied by the other poles of the system. Now, if I do that, and I have Z minus 1 to the N, I'm going to call this N the system type. Now, this is similar to what we've done in the continuous time. If you remember, in the continuous time, we wrote this as 1 over S to the N, and we called N the system type. Here, we're going to write it as, or we're going to factor out Z minus 1 from the denominator. And of course, we're going to factor out Z minus 1 in the denominator if there is N, and we're assuming there is no Z minus 1 in the numerator. Otherwise, we can cancel them out and then see what remains after we cancel all these Z minus 1 in the numerator. I hope that makes sense. So again, we're assuming that Zi is not equal to 1, because if it's equal to 1, it's going to cancel with Z minus 1. This becomes N minus 1. And we assume also P sub J is not equal to 1. So there is only all the Z minus 1 terms are together, and they are to the power of N. N is called the system type. Okay. And we'll see. I mean, we'll clarify what that means when we do an example. Now, if you look at the DC gain of the open loop plant G of Z, the DC gain is given by K DC is equal to the limit of G of Z as Z goes to 1. The DC gain, I think we mentioned this in the homework help, is the value of G of Z when Z is equal to 1. Similar to how we calculate the DC gain for continuous time system, G of S when S is equal to 0, that will give me the DC gain. Okay, So if we have a type 0 system, if I look here, if n is equal to 0, which means g of z does not have any terms that is z minus 1 to the n. In this case, this is a type 0 system. KDC is finite and is given by KDC is equal to k, the multiplication of 1 minus zi divided by the multiplication of 1 minus pj. Again, we substituted z equal to 1. Again, we took g of z from here and we substituted the limit as z goes to 1. I'm going to have k multiplied by 1 minus zi, the multiplication of these, divided by the multiplication of 1 minus pj. So therefore, I'm going to have k, the multiplication of 1 minus zi, over the multiplication of j equal 1 of 1 minus pj. Now, if n is greater than or equal to 1, this DC gain is going to be infinite. If n is equal to 1 or greater, when I take the limit as z goes to 1, I'm going to have 1 minus 1 in the denominator. And therefore, this KDC is going to be infinity. So therefore, this DC gain is going to be infinite because the plant would have had integrators in it, pure integrators, that is going to result in an infinite value for KDC. So therefore, we can calculate the steady state error as the limit as k goes to infinity of E of k using the final value theorem. What is the final value theorem? From Z transform properties, the final value, E steady state, is going to equal to the limit of E of k as k goes to infinity, which is going to equal the limit as z go to 1 of z minus 1 multiplied by E of z. This is the expression for the final value theorem. This is coming from the final value theorem. From final value, the expression for the final value in the final value theorem. So this is the limit of z minus 1 of E of z as z goes to 1. So therefore, if I plug in what E of z equal to from what we calculated here, or here, E of z is over Rz is equal 1 over 1 plus g of z, and therefore the steady state error is going to equal to z minus 1 over 1 plus g of z multiplied by R of z. Again, this comes directly from here. E of z is R of z over 1 plus g of z. Okay. So let's look at what happens for different inputs that we apply to the system and what is the value of this steady state error. Now, just a word of caution that we can use this final value theorem that we just stated here, provided that all the poles of E of z are inside the unit circle, except for possibly a simple pole at z equal to 1. So if we have poles that are outside the unit circle, this means the system is unstable and therefore the final value is not going to exist. And therefore we have to check, make sure that E of z, all the poles are inside the unit circle. Okay, so let's see what happens since we got this expression here, and this expression for the steady state error is in terms of R of z. Let's see what happens for different R of z, what the expression or what the steady state error is going to equal to. So the first case we're going to look at is when we have a unit step input. If I have a unit step input to the system, then R of t is equal to a unit step. R of k is going to also be the discrete unit step. R of z is going to equal to z over z minus 1. And therefore, if I look at the steady state error, according to the expression, is going to equal to the limit of z minus 1 as z goes to 1 of 1 over 1 plus g of z multiplied by z over z minus 1. This is r of z. Z minus 1 with z minus 1 is going to cancel. And since I'm taking the limit as z goes to 1, this z becomes a 1. And therefore, this is going to equal to 1 over 1 plus the limit as z goes to 1 of g of z. Now what we're going to do is we're going to define this limit of g of z as z goes to 1 as the position error constant kp. So therefore, the steady state error can be expressed as 1 over 1 plus kp, where kp is equal to the limit as z goes to 1 of g of z. And this is the position error constant. Okay, so therefore for the case when n is equal to 0, where kdc is finite, the steady state error is gonna equal to 1 over 1 plus kdc. So if we calculated the kp, which is the limit as z goes to 1 of g of z, and this came out to equal to kdc. This is the dc constant because we're substituting z equal to 1. So if this is the value of the limit of g of z as z goes to 1, then the steady state error is going to equal to 1 over 1 plus kdc. Okay. Now what happens for the case when n is greater than or equal to 1? In this case, the steady state error is going to equal to 0 because the kdc is going to equal to infinity. And therefore, for the case when n is greater than or equal to 1, the steady state error is equal to 0. Okay. Now the second case, the second input we're going to look at is what happens when we have a unit ramp input. And in this case, r of t is equal to a t, r of k is equal to k multiplied by t, and therefore r of z is z multiplied by t over z minus 1 squared. And in this case, the steady state error, the limit of z minus 1 over 1 plus g of z multiplied by the input zt over z minus 1 squared. Z minus 1 with z minus 1 is going to cancel. This is going to equal the limit of t multiplied by z over z minus 1 if I multiply the denominator, z minus 1 plus z minus 1 multiplied by g of z. And what is this equal to? If I substitute z equal to 1, I'm going to end up t multiplied by z is going to just equal to a t. And z, if I substitute z equal to a 1, this term is going to equal to a 0. So I'm going to end up with t divided by z minus 1 multiplied by g of 0. Now we're going to do the same thing. We're going to define a velocity error constant. And the velocity error constant is defined as the limit as z goes to 1 of 1 over t multiplied by z minus 1 multiplied by g of z. And therefore, the steady state error from here is just going to equal to 1 over kv. Okay. Now since we wrote g of z using this form, if n is equal to 0, then kv is going to equal to 0. Again, this is kv is equal to z minus 1 multiplied by g of z. If n is equal to 0, it means there is no z minus 1 in the denominator that will cancel with the z minus 1 that I have here. And therefore, kv is going to equal to 0. And therefore, the steady state error, which is 1 over kv, is going to equal to infinity. If n is equal to 1, so if here n is equal to 1, then this z minus 1 that I have in kV is going to cancel with the z minus 1 that I have here. And in this case, I'm going to get a kV that is finite and non-zero. And in this case, the steady state error is just going to equal to 1 over kV. If n is greater than or equal to 2, then I'm going to have in the denominator here z minus 1 squared. And when this multiplies by z minus 1 is going to cancel with 1 of the z minus 1 that is squared or higher. I'm going to still have z minus 1 in the denominator. And when I substitute z equal to 1, I'm going to get kV that's going to equal to infinity. kV is going to equal to infinity because z minus 1 is cancelled and is going to equal to g of 1. And g of 1, if I have z minus 1 square or higher, one of them cancelled with the z minus 1 in the expression of kV, but I will still have z minus 1 in the denominator. And therefore, when I plug in z equal to 1, I'm going to get kV that is equal to infinity. And in this case, the steady state error, since it is 1 over kV, is going to equal 1 over infinity, which is going to equal to 0. So to summarize all that, similar to what we've done with continuous time system, if the system type is 0, then for a step input, the steady state error is going to equal 1 over 1 plus Kp. For a ramp input is going to equal to infinity. If the system type is 1, the step input steady state error is going to be equal to a 0. For a ramp input is going to equal to 1 over Kv. If the system type is second order or higher, then for a step input, the steady state error is 0. For a ramp input, the steady state error is 0. And we define Kp as the limit z goes to 1 of g of z, and Kv the limit as z goes to 1 over t multiplied by z minus 1 multiplied by g of z. Okay. Let's do an example. So in this example, we have a system Gp of s, 1 over s plus 1, 0 older hold, and we have a constant. And therefore, the discrete time equivalent system is going to be k multiplied by g of z, and g of z here includes the 0 older hold, and this is the input, the output. G of z is going to equal to the z transform of 1 minus e to st over s. This is the 0 older hold multiplied by g of s, which is 1 over s plus 1. 1 minus e to negative st is going to give me 1 minus z to negative 1. And then I'm going to still have an s that is going to multiply by s plus 1. So the z transform of s multiplied by s plus 1. Either using the residue method or using the table that we have at the end of the book, we can get the z transform, and it's going to be the expression here. This is the z transform. That is the result of this. 1 minus z to negative 1. I can write this as z minus 1 over z. Multiply them together. Z with z is going to cancel. Z minus 1 is going to cancel. I'm going to end up with 1 minus e to negative t divided by z minus e to negative t. So this is my g of z. Now if I look at this g of z, what is the type of the system? This system is type 0. If I look at g of z, there is no z minus 1. Z minus 1 is to the power of 0. There is no z minus 1 in the denominator. And therefore, this is type 0 system. And so the steady state error, according to this table that we derived, this is type 0 system. For a step input is going to be 1 over 1 plus Kp. For a ramp is going to be infinity. Okay. So let's calculate the steady state error for a step input. In this case, E of z is equal to 1 over 1 plus k multiplied by g of z using the final value theorem. the limit z goes to 1 of z minus 1 over 1 over 1 plus k multiplied by g of z, and this is gonna equal z over z minus 1, which is gonna equal, multiplied by z over z minus 1, which is gonna equal to 1 over 1 plus k. Why did I have to do this? I did not have to do this. I can just calculate this. We can calculate this directly using we could have calculated this directly using the KP. Okay. Now for ionic ramp input, the steady state error is going to equal to the limit as z goes to 1 of z minus 1 multiplied by 1 over 1 plus k of 1 minus e to negative st over z minus e to negative t, which is equal to z multiplied by t over z minus 1 squared. And therefore the limit as z goes to 1 is going to equal to 1 over 1 plus k multiplied by t over z minus 1. In this case, this z minus 1 and z minus 1 cancel, and therefore the steady state error is going to equal to infinity, because this is the calculating it directly. Or if you want to use the table summary that we calculated, we can calculate the steady state error is equal to 1 over kv, and kv is equal to the limit of 1 over t multiplied by z minus 1 multiplied by k multiplied by g of z, and this is going to equal to a 0 because g of z does not have in the denominator z minus 1, and therefore kv is equal to 0. The steady state error is equal to 1 over 0, which is equal to infinity. Okay. Okay, so I'm going to go back to the calculation of the steady state error for the case of a unit step input. So we calculate it using deriving it directly using E of z. Now let's calculate it using the table. So according to the table here, the steady state error for the system is going to equal to 1 over 1 plus kp, and kp is equal to the limit as z goes to 1 of g of z. So here we can calculate kp, and kp is going to equal to the limit as z goes to 1 of g of z. Now what is this limit equal to? Let's look at g of z. G of z we calculated is equal to 1 minus e to negative t over z minus e to negative t. So here this is going to equal to the limit as z goes to 1 of 1 minus e to negative t divided by z minus e to negative t. Now one thing that we have to, I don't want to confuse anybody, but here we have again k in the system that I took out of k of g, a k that I took out of g of z. Now when I calculate the steady state error, I'm going to have to account for all the gain in here. So this k, I could have originally included it with g of z. So when I calculate now the steady state error, I'm going to calculate k multiplied by g of z. Does that make sense? So here we separated them, but what I could have done is I could have taken g of z that we calculated here and just multiplied it by k. So let me do this here. So the equivalent of this system is going to be y of z, and this is g of z, and then I have a k, so it is k multiplied by 1 minus negative t divided by z minus e to negative t. And therefore, when I calculate the error here, I'm going to add a k here. This k, I mean, if k is equal to 1, I won't have to worry about it. But if there is a gain in the system, I have to include it with g of z. So let's call this, I mean, since this is g of z, we redefine g of z to include this k that was in the gain. Now what is the limit as z equal to 1 of this system? This is going to equal to k multiplied by 1 minus e to negative t divided, if I substitute z equal to 1, this is going to equal 1 minus e to negative t, and therefore this and this is going to cancel, and I'm going to have a k. And therefore the steady state error according to the table is going to equal to 1 over 1 plus kp, but kp is equal to a k, and therefore it is 1 plus k. Okay, I hope I did not confuse anybody, but nevertheless, I mean, I want you to pay attention, like when we solve a problem and we do the calculation, we did all this calculation for g of z, this assumes g of z includes all the gains in here. So I could have, you know, done this differently by just taking the k and combining it with g of z here, and then I will have the k that will multiply all the g of z factors here. Okay, so that's it for this module. If you have any questions, please let me know. Thank you, everybody.